All right, physics, here we go again. Part 2 of electromagnetic induction. We'll look at Lenz's law. So we saw in the previous lecture that all you need to do is move a magnet near a coil. If you change the flux in the coil, you're going to induce an electric current. And in fact, you could even do it by pulling the magnet away. That would also change the flux. Increases, decreases, doesn't matter. In any case, a current gets induced here so long as there's a change. And that sounds pretty great. All I got to do is move a magnet towards a coil and I get electricity. That's amazing. Today we learned that you don't get that induced current. You don't get that electricity for free, in a sense. You do have to do some work. You have to put in some effort. You can't just swing it there against no opposing force. So that's where we get to Lenz's law. So just to summarize, we defined this quantity magnetic flux, which quantified the amount of magnetic field through a coil. So we needed all three of those quantities to get the idea of magnetic field through the coil. And we measured it in Webers. And we have Faraday's law, which said the rate at which you change it, the more quickly you change the flux, the rate of change of flux, the bigger the voltage you get. And the more loops you have, the more voltage you're going to get. Today we talk about why is there a negative sign out here? Why is there a negative sign? And Lenz's law describes why that negative is there. And the Lenz's law is just one sentence. When I read it to you, it's going to sound like gibberish the first time, but we're just going to practice applying this law over and over again in this lecture, and hopefully by the end, what sounded like gibberish at the start will make sense by the end. Here it is. So Lenz's law says, the current produced by an induced EMF flows in a direction that opposes the change in flux that caused it. Pause the video, read it one more time for yourself. It is weird, but let's see if we can make sense of that. Current produced by an induced EMF, so these induced currents, the induced currents will go in a direction that opposes, that fights against the very change that caused it. So here's a magnet, and in a moment we're going to push that magnet upwards, which will change the flux through this single loop. At the moment, there's the area of my loop, and the magnetic field is upwards. So there's magnetic field in the upward direction through this area. As I move that magnet up, that's going to increase the upward magnetic field through the loop. That's going to be an increase in the upwards direction. So the coil is going to, that's a change in flux, so a current will be induced. The direction of the current will be such that it fights against this change. So it's like the loop's going to go, hey, you're increasing my magnetic field upwards. I don't like that. I'm going to fight against it. And so the current that gets induced will have its own magnetic field, as we know, and it will be a magnetic field that fights against. So it looks something like this. So we push that magnet up, current gets induced, the current spins, I guess that's clockwise, and so the magnetic field around the current is downwards. So it would push against that incoming magnet. And the reverse is true. When you pull the magnet back out again, the coil's like, hey, you're decreasing my flux upwards. And so the current flows in the opposite direction to create what's being lost. I'm losing magnetic field upwards. I'll create my own magnetic field upwards so that the flux through the coil stays the same. Let's read it again, see if it makes any sense. So the current that gets produced by an induced EMF will flow in a direction that opposes the change in flux that caused it. try another one. So imagine you drop your wedding ring through a magnetic field, and we're going to track this ring through its journey. Now, as it's falling through the air, not through any magnetic field, well, there's no new magnetic field going through the coils. There's no change in flux there. So of course there's no induced current. As soon as it begins to fall into that magnetic field zone, now previously it was just here, no flux, and now there's two little dots like out of the page. So the flux out of the page has increased. That's a change. And the current is going to fight that increase. So I think of it as I just gained these two dots, these two fields out of the page. So the current is going to be induced that produces two crosses, two field lines into the page. The current that's induced will oppose that. So that, two dots plus two crosses is 0, which is what I want. I don't want there to be any change. I want to stay with what I had. So now what direction would the current flow in order to make that? You should bust out your right-hand rule and figure out which way would the current go, clockwise or anti-clockwise, to create those two magnetic field lines into the page. If you said that way, you did good. Now the current would flow anti-clockwise. Now what about as it's falling through? Well, now as it moves from like here to like a little bit below there, nothing changes. It's got 4 lines out of the page, and as it moves, it's still going to have 4. So no change in flux, so there'll be no induced current, only on entering. But then what about when I leave, as I fall out the bottom? When I fall out the bottom, I previously had 4, now I'm going to go down to 2 as I drop out of that page. My flux out of the page is going to decrease. That's a change as well. And so the current that is induced will oppose the decrease. So it will create a magnetic field out of the page. It's going to try to create its own 2 little field lines out of the page so it looks like what I had before. So there is no change. So which way would the current flow to create those 2 little field lines? You have to bust out your right-hand rule and figure that out. And if you said that way, you did good. And then, of course, as I fall to the floor, there's no change in flux there, so there's no induced current. So I'm going to give you lots of examples with these loops of current, and you're going to have to figure out which way would the current flow. And so it's worth reviewing that right-hand rule. Remember, if you go and grab a wire, and put your thumb in the direction of the current, then your fingers curl through and show you the direction of the magnetic field. So you can imagine you're just holding onto it, and if your thumb is pointing in the direction of the current, then your fingers will show you the direction of the field. A lot of people like this method. I actually prefer a different one. I borrow from the grip rule that we used for solenoids. Remember, for solenoids, you switch the definition of what your fingers and thumb mean. So instead of fingers for field, we make fingers for current, because look at those little lines. They look like fingers. So you grip the solenoid, and then your thumb shows you the direction of the current. You can borrow that and use that for these single loops as well. So if I know that I want there to be a magnetic field into the page, I just swing my thumb into the page, and now my fingers curl in the direction that the current must be going. If I know I want a magnetic field out of the page, I just point my thumb at me, and now my fingers curl in the anti-clockwise direction, showing me the direction of the current. So I find this one handier, but use whatever works for you. Let's try another one. So imagine I drop a north pole towards a ring, a loop of current. As that magnet gets closer and closer to the ring, that's going to be an increase in flux. It's going to be an increase of flux into the page from this perspective. A north end will be increasing into the page. So what's the current going to do? It's going to fight that. It's like, hey, there's a magnet coming towards me, and it's increasing my flux. So it's going to try to stop that magnet. It's going to oppose that change. It's going to oppose its falling towards it. It's going to have to create a magnetic field to fight against it. So if there is lines coming at it, it's going to have to create. Oh yeah, so those green ones would be, if you like, that's what's coming at the coil, right? That's what's coming out of the north end of that magnet into the page. The current is going to oppose that, so it's going to put a magnetic field in the opposite direction, my little dots there, to try and fight against that. So which way would it go? Well, for me, to create those little red dots, I point my thumb at me, and that tells me that the current should flow anti-clockwise. Now, does this actually happen in real life? Like, does the magnet really get opposed from falling towards the ring? Yeah, it does. Check this out. This is a whopping big copper ring, and this is a really strong magnet. And he's just going to drop that towards that ring, and you watch what happens. It's pretty awesome. It doesn't just fall through at 9.8 meters per second. No, its motion is opposed. And it looks unreal. It looks crazy. It falls slow because there is an induced current in that copper ring that's trying to oppose the change in flux that this magnet represents. And so he can flip it around like that, and the current will always just try to stop it from moving. Stop changing my flux, magnet. The current will always just try to oppose any change. So what's going on there? As that magnet falls towards the ring, the current fights against it. It doesn't quite have, the current can't flow quick enough to perfectly prevent that magnet from falling, so it does eventually get through. Now, what if we supercooled that copper ring? If we dip that copper ring in liquid nitrogen, you should remember that as metals get colder, they generally get better. Conducting, their resistance decreases. And so the current, the induced currents, the ones that are opposing the change in flux, they can flow really fast. So when it's really, really cold, it can almost stop the magnet. Check this out. This is this conductor has been dipped in liquid nitrogen. We drop the magnet towards it. It almost stops it completely. Not quite. And then notice on the way out, so it goes at a constant velocity once it's inside, and then on the way out, it almost stops it again, because it's a change on the way in, it's a change on the way out. If there was such a thing as a perfect conductor, we could do some pretty cool stuff. So here's what happened just then. If you had a perfect conductor, you would be able to oppose it completely and send it back to where it came from. Like, hey, I'm happy with my flux, go away. If you had a perfect conductor, that would be pretty awesome. And we actually kind of do have that. So we've discovered superconducting materials. So this flying disc here is a metal that is superconducting. So there's no resistance to current, and it's floating above a magnetic track. And as soon as its inertia tries to carry it off the track and in a straight line, the superconductor is like, whoa, that's a change in flux, and a current gets set up to oppose that change. Like flying off the tracks would be a decrease in flux for it, and so a current gets set up that opposes that change, and so it stays continually the same height above the track. There's no opposition to sideways movement other than air resistance. So it's pretty darn cool. So we're going to have magnetic levitation with these perfect superconductors. I put a link in Connect of other cool videos like this, just because floating magnets are awesome. Let's try another one. Keep practicing Lenz's law. So let's imagine you have a coil and you stretch it. So it goes from having pi r squared to whatever that is, less area. Right? That's that's a decrease in area, which would cause a decrease in flux. In this case, a decrease of flux into the page. So the coil is going to be like, hey, I used to have lots of magnetic field into the page, now I have less. So it will try to create more into the page. So I shove my thumb into the page and my fingers tell me that it's going to, it's going to try to create more into the page to offset the loss. Current will flow that way. What about this one? I rotate my coil 90 degrees. So this is the maximum amount of area that coil could have. If you rotate it 90 degrees, you go down to 0. So that's definitely a decrease in flux. That's a decrease. I'm losing flux that is into the page. And so that coil is going to be like, I want to have flux that goes into the page. It will try to create some. So the current will be induced to oppose the decrease, which would be thus, meaning it tries to create these into the pages that it's losing. Which way would that be? Put your thumb into the page and you should see that it's clockwise. Let's do one more. I think I've got lots more actually. Hopefully you're trying to predict this at home, right? You've got your hand in front of you and you're actually practicing this stuff. So if I grab that ring and I yank it out of that magnetic field, that's going to be a decrease out of the page. I'm losing flux out of the page. So it will try to create some into a page to offset the loss. Current will be induced to oppose the decrease, so it'll try to create some. And that will be, put my thumb towards me, it's going to go anti-clockwise. What about this one? I have a magnet side onto the loop and I move it closer. Well, at the moment, none of those field lines are passing into the loop. And so moving it back and forth doesn't do anything. So there's no change in flux, there's no induced current there. Here's a slightly trickier one. Imagine you have a wire and it's carrying a current and the current is increasing. Now we know that around a wire, you have a magnetic field. Use your right hand rule. So grab the wire, go and grab it with your thumb pointing to the left, and your fingers will be going into the page above the wire, and as you curl around, they'll be coming out of the page below the wire. That's what a steady current would look like, and to represent an increasing current, I just animated it like this. So imagine the current's getting bigger and bigger and bigger and bigger, so the magnetic field is getting bigger. Usually we would draw more field lines, but hopefully you get the idea, right? That's an increasing current. So what about this loop? What is it experiencing as this current increases? Well, hopefully you can see it's getting more magnetic field into the page. It's an increase in flux into the page. So the loop will obey Lenz's law. It's going to be like, hey, I don't want to have an increase in flux into the page. I will oppose that. So the flux increases into the page. It's going to try to create the opposite, fight against that. So it's going to have a current this way. See if you guys can predict what's going to happen for the other 3. So you should just pause the video now and see if you can predict which way the current will flow in these 3 loops. So pause the video. And hopefully this is what you predicted, right? As that current decreases, that's going to lose flux into the page, and so it will try to create some into the page, so it will flow clockwise. Constant current means there'll be no change in flux, so there'll be no induced current. And then the last one, as that flux increases, that's an increase out of the page, so it'll fight against that increase by creating a field out of the page, which would be clockwise. Hopefully you did really well there, hopefully getting the idea. So we can use this idea of opposing currents that oppose the magnetic flux that changes it to create like levitation. So notice that is plugged into the alternating current. So there's just like that's a coil of probably hundreds of turns there with an alternating current. So there's an ever-changing magnetic field coming out of that black square thing. And so there'll be an alternating current in here that opposes that. It'll set up its own magnetic field to be like oppose the change in flux that's occurring. We can use that to make weapons, actually. And I don't know how good they'd be, but I put a link in the description. If you put a ring over a coil, an iron rod will just condense that magnetic field, close the switch, that electromagnet will kick in, be a strong magnetic field, and in the metal ring it'll be like, hey, the magnetic field's changing in me, I will oppose it, so those two magnetic fields will oppose, and the iron ring, or the ring will fly off. Yeah, check out the video and connect. So here's what we've done so far. We saw magnetic flux. Faraday realized if you change the flux, you can induce currents. The size of the current is proportional to the rate of change. And Lenz's law tells us, well, the direction of the current will oppose the change in flux. All right, hopefully you tracked with me. This is what you've got to do. You need to read 6.3, have a go at the questions. This is optional. I'm going to give you a lesson at the end of the week to do that. But you should try to do this as well. Happy quarantine, guys.